Hi, welcome back to our webinar series, which enables us to use class time more efficiently. In this, we're going to look at centripetal force, why objects move in circles. This was developed by Sir Isaac Newton and is perhaps one of the biggest ideas of all. By the early 1600s, before Newton's time, it was well known that the moon orbited the Earth and the Earth orbited the sun. The relative orbital distances and periods of the major planets were known at this time. However, Isaac Newton asked the question, why does this happen? To answer the idea of why the moon orbits the Earth and the planets orbit the sun, he wrote this book called the Principia. In this, he proved 3 laws of motion, which we studied during the first semester, centripetal force, which we're going to study now. He developed calculus, to breaking things up into little parts, and he also developed the law of universal gravitation. Of course, this was all in a very dense Latin. Isaac Newton set forth his theory of circular motion and universal gravitation in a very logical step. He began with his 3 laws. Since he was 21 when he developed this entire theory, he had to rely upon the work of others that had been done. The first law came from Galileo's moving experiments. Objects at rest stay at rest, objects in motion stay in motion. This allowed for a moving Earth. Things don't fly off the Earth because everything is moving, and the Earth stays moving because it was moving yesterday. The second law, F net equals ma, came from Johann Marcus Marci. He was personal physician to the Duke of Bohemia, and he borrowed one of the Duke's artillery crews and had them fire cannonballs into one another. From this, he proved that acceleration was inversely proportional to mass. This allowed Newton to say that unbalanced force changes motion. The Earth wants to go straight, however there is an unbalanced force of gravity which will now cause acceleration in moving the Earth in a circle. The third law was Newton's own conception, that of equal and opposite forces. Just as an Earth would pull it downward, it's also going to pull the moon downward. Similarly, the moon and the apple will pull up on the Earth with an equal and opposite force. We see this demonstrated in tides. Newton's 3 laws can be used to explain the motion of the moon around the Earth. The Earth wants to go straight because of inertia, as we can see right here. However, there is an unbalanced force of gravity. Nothing connects the Earth and the moon, so gravity pulls the moon inward. The moon again wants to go straight because of inertia. Gravity pulls it inward. The moon wants to go straight because of inertia. Gravity keeps pulling it inwards, in nice Iolani colors, of course. Wants to go straight because of inertia. Gravity pulls it inward. It wants to go straight because of inertia. Gravity pulls it inward. Again, we get the picture that Earth wants to go straight because of motion. Gravity pulls it inward. This is an unbalanced force, a net force, which is causing acceleration and a change in direction. Looking at this in a much prettier fashion, the result of this is a circle. Of course, Newton broke this down into tiny little pieces. He had his theory of calculus as well. From this, we can see that there's unbalanced forces and equal and opposite forces. The Earth is pulling the moon down, but the moon is pulling the Earth up, as we can see in tides. Essentially, this force of gravity, unbalanced, is moving the moon in the circle, so we can say gravity is providing the centripetal force. Isaac Newton named this centripetal, literally center walking or center seeking force, because it always pulls inward, as we saw from our bowling ball challenge. The one thing to think about, some of the other words, pedestrian is the same root word as the center seeking or walking. So again, we see some of these words around us. From this, moving objects naturally want to travel in a straight line at constant speed. We can think about this again, the first law. The second law was an unbalanced force, hence gravity, causes there to be a change in speed or direction. Therefore, When it's moving in a circle, there's net force, and we call the special net force that moves us in a circle centripetal force. Because it is a net force, some combination of forces must cause it. Uniform circular motion means the object is moving in a complete circle and it's perfectly uniform in terms of force. We had some historical background as well as concepts. Now we'll look at some technical terms of universal circular motion. Anytime an object changes either speed or direction, there's a change in velocity and hence acceleration. We need to make the distinction. Tangential acceleration is the change in speed. If an object is moving in a given direction, tangential acceleration, the velocity at any moment is tangent to the circle, and acceleration that is parallel to the velocity will cause it to speed up or slow down. Centripetal acceleration, however, is the change in direction. In this case, an object is moving along in a straight line, and centripetal acceleration will pull it perpendicular, causing it to change its direction. We'll consider how our change in direction actually changes. We'll consider a velocity v2, which I've sketched out the vector over here. Now we want to see, how did this vector change? To evaluate, we're going to lay our vectors head to tail to try and figure out how did our velocity change. v2 minus v1 will give us a change in velocity. So here we have v2 drawn as it is. v1, we take the negative of the vectors, giving us v2 minus v1. When we look at the actual acceleration or the change in velocity, we note that our change in velocity is inward directed. We could go through calculus. If you want to know the answer to this, you can either look it up online or talk to me. But the centripetal acceleration, we calculated as v squared over r. Therefore, an object goes twice as quickly with the same radius. You have 4 times the centripetal acceleration. If it has twice the radius with the same velocity, you only have half the centripetal acceleration. We remember that any time there is acceleration, with changing in velocity, acceleration is caused by a net force. We can now think about Fc is but a very special case of the net force. Any combination of forces can provide the centripetal force. That might be tension, that could be gravity, pulling the sensor around, or it could be the friction of a car tires. There is no centripetal force in and of itself. Any combination, however, can provide centripetal force. Let's look at how this actually works out. Remembering that the unbalanced force, the sum of all the forces, cause there to be a net force, which causes acceleration. We'll then look at the one idea that this net force we can specially call Fc, which will cause there to be our special centripetal acceleration. There we go. Anyway, tomorrow in class we'll practice this both qualitatively and quantitatively. Thank you very much.